Loud.
This meeting is being recorded.
Great. Okay, perfect. Well, thanks everybody. Welcome to the October Govys. And we're very happy to have Dakota Arthun, if I'm saying his name correctly, from the US Census Bureau. He's going to give us a talk on record linkage. And just a little teaser, next month we will have Ted Enumerated joining us. He's going to give us a talk on our package fastLink. So we'll have more on record linkage in November. And several months ago, we had Robin Lineker, the developer of Splink, who gave us a tutorial too. And that recording is on our Govys YouTube channel. So I am going to turn my camera off. I will pass the podium on to Dakota. I will let him introduce himself. And Dakota, do you want people to, well, I guess they can't interrupt you because we're on an actual webinar. So people could put questions in the chat or in the Q&A. And Dakota, did you want me to interrupt you during the talk or hold questions until the end?
Yeah, feel free to interrupt me. This is more casual, so feel free to interrupt me. If you guys have questions along the way, feel free to ask.
Sounds good. Okay, so I will pay attention to the chat and the Q&A and pass things along as they come up. All right, well, thanks everybody. And Dakota, I will turn my camera off and let you start your presentation.
Awesome. Yeah, thank you guys for having me, our Govys group, and Wendy and Yves for recommending this to put this together. So just to give an introduction, so what I'm going to be talking about today is comparing open source record linkage software to existing approaches using census data. Kind of the background on this is, as was just mentioned, record linkage is done at the US Census Bureau for a variety of different uses. And over the past couple of years, as I just mentioned, fastLink and Splink had come out as open source software that could be potential alternatives for record linkage software that we wanted to test against. And so that's kind of what we ended up doing. And this is what I'll be presenting today. First, I wanted to say thanks to my collaborators, Aaron Guillory, Sarah McGinnis, Julie Zamora. So just a standard disclaimer real quick, that the opinions expressed are mine and not that of the Census Bureau. And then also that the numbers that I'll be presenting today have gone through disclosure review, have been noise injected. So to kind of alleviate any concerns of showing any titled data. And to give an outline of what we'll be talking about today, so I'll give you guys a little bit of a background of record linkage done at the US Census Bureau. I'll jump into some details about the Fleggy Center method for record linkage. And then I'll jump into this application that we did with deduplicating blocks of e-sample person records that were created during the 2020 Post-Enumeration Survey. And then we'll end on a discussion / some conclusions, and then also, since this is our Govys, I'll show a demonstration using the fastLink library to a toy data set. We can kind of see how fastLink actually works when being applied to some data. So some background of record linkage at the Census Bureau. So there's a couple of applications, a variety of different applications that we've used record linkage for, but I'll kind of outline two just to give you guys a taste of what is done at the Census Bureau. So an instance of, say, matching a file of Decennial Census respondents to itself would be kind of a deduplication task. So namely, this kind of sets up how big the record linkage can get at the Census Bureau for kind of, say, matching around 350 million records to the other 350 million records. So a big problem. An example of a matching would be matching, say, an independently surveyed group of people to the sampled kind of subset of post-enumeration respondents. So In this case, for the Post-Enumeration Survey, the size of record linkage is kind of smaller. It's around in the 500,000 records being matched to the CUF, the census unedited file, which is in that nation-sized file. And the record linkage that we do is all based around this Linkage Center framework. So the Linkage Center framework, it was originally introduced in 1969 as a method of record linkage that has been proven to scale to these large data sets. And we're going to be comparing the following software that implement the Linkage Center framework in kind of slightly different ways that I'll kind of outline. So our baseline at Census is this BigMatch software. So BigMatch is a C-based application that implements the Linkage Center framework, and it continues to be used at Census today. As mentioned, so fastLink is an R library that was developed by Ted and Horado back in 2017, and it also implements this FS framework with the expectation maximization algorithm, which is an unsupervised learning algorithm to produce these matching parameters. It also includes kind of this other parameter that accounts for missing data. So when you're matching some attributes in a record, in a person record, may have missing information. For example, the middle name might not always be filled in a survey. The other part about fastLink that kind of provided notice or like how it could be an improvement is it allows for parallel computing at the block level. And then after fastLink came out, Splink is this Python package developed by Robert Lineker at the UK Ministry of Justice. And it expands upon fastlink's implementation of the Linkage Center framework with parallel computing leveraged by these SQL backends. And it also included a couple of nice pre-processing tools that were, help you visualize the data before you even jump into the record linkage. So you can look at kind of missingness of the data's matching attributes or kind of certain counts on how the data looks before you even jump into doing the matching itself. And this is going to be a quick, kind of quick and dirty explanation of the Linkage Center framework. So imagine that you're given a file A with NA records and another file B with NB records, and you want to match file A to file B. What you do is you construct this decision space, gamma, where gamma is this mapping of the Cartesian product of the records in file A cross records in file B with this decision function gamma. And to go into detail about how gamma works is it's a mapping. It maps the pairwise comparison of, say, a first name attribute to some value between 0 and 1. 1 meaning that it's full agreement, and 0 meaning that these two named characteristics disagree. We can also kind of establish this problem as a binary classification problem with establishing these two latent classes, the M subset and the U subset. So the pairwise comparisons that end up in the match subset, and the U, the pairwise comparisons end up in the unmatched subset. So A cross B can be represented as the set of pairwise comparisons that are deemed matches, and then the set of pairwise comparisons that are deemed not matches. We match across K matching attributes in a record, and so an attribute would be considered like a first name, a middle initial, last name, month of birth, date of birth, sex, and we have to define these match probabilities. In record linkage, these are these M's and U's. The probability of given the positive agreement pattern that the pairwise comparison lands in the match set. And these N's and U's will be learned using the expectation maximization algorithm for fastLink and for Splink. And for BigMatch, what we've did as a baseline is we use the legacy matching parameters that we'd established at the Census Bureau over several decades. One last parameter that I wanted to mention is this lambda value, which is just the given any pairwise comparison of a record, what is the probability that those two records actually land in the match set? And so looking at those kind of values that I described on the previous slide, we can construct the likelihood equations for BigMatch and for fastLink. And yeah, there's some math here that I want to kind of dive into a little bit, but there's some distinctions between how BigMatch is doing record linkage versus how fastLink is doing, fastLink/Splink is doing record linkage. So for BigMatch, we get a product of K across the K matching attribute with these Bernoulli distributions, where we have our M's and our U's, the match probabilities and unmatched probabilities. And what is done slightly differently with fastLink and Splink is instead of having either a full agreement, full disagreement, you get these pi k's for level of agreement. And those levels of agreement are determined using the Jaro-Winkler fuzzy string comparator, and given how those string scores vary across. So if a string comparison is completely different or somewhat similar or nearly identical. So you can identify these levels of agreement and then run its EM algorithm to determine those probabilities associated with those individual levels for that particular attribute. The other distinction between BigMatch and Splink is this delta in the exponent. And that delta is this missing value indicator that takes on a 1 if there's missingness in that matching attribute, and 0 otherwise. And kind of to relate it back to BigMatch, when we're doing record linkage with BigMatch, we have to manually specify that if there's missingness in that matching attribute, whether or not we should give a full disagreement weight to that component's contribution to the match score, or if we give a 0 weight to it. So it's kind of a technician's decision to handle missingness in given matching attributes, whereas fastLink and Splink kind of handle that with this delta term. Going into detail with the fuzzy string comparator. So when you're doing fuzzy comparison with the first name or last name or any kind of string attributes that you're comparing on a record, fastLink and Splink kind of do it slightly different from how BigMatch does it. One of the advantages of fastLink and Splink is that they allow you to choose between different string comparators, whether you want to use the Jaro-Winkler or the Levenstein fuzzy string comparators. And as I was saying, fastLink's default is to have these 3 levels of either full disagreement, somewhat similar, or very similar. And those thresholds are set based off of the string comparator fuzzy score. So for string comparisons that are less than 0.88, it lands in the disagreement probability, versus between 0.88 to 0.94, it'll be given that partial level probability of agreement. And then if the fuzzy string comparison is greater than a 0.94, then it gets that full agreement probability. This is different from how BigMatch does it. So BigMatch, it only uses the Jaro-Winkler string comparator. And what it does is it maps the Jaro-Winkler score piecewise linearly, kind of this little graph is outlining how it does it, between the full disagreement weight and the full agreement weight. And so as that Jaro-Winkler score becomes closer and closer to 1, the partial weight that is added to that component's contribution to the overall match score increases. Wendy, I'll pause real quick. Is there any questions, or should I keep going?
I haven't seen any questions yet. Although maybe I have a couple questions. Could you go to the previous slide?
Mm-hmm.
So does this mean that oh good, one person raised their hand. I'll come to that person. So does BigMatch then in the comparative, so say you're comparing on last name. So is it either a 0 or a 1? That component matches or doesn't match? Is that?
Yeah, so when you're learning the M's and the U's in that sense for BigMatch, the Jaro-Winkler score is going to be a value between 0 and 1. And really actually how BigMatch produces its output is it doesn't produce its output as a posterior score, like in the likelihood equation. It actually produces a match score, which is made by this log odds equation. And so that's why actually we have this piecewise linear mapping from the disagreement weight to the full agreement weight is in order to give like partial weight to the match score in say like the last name, we rely on this piecewise linear transformation to transform the Jarl-Winkler score to land somewhere on this line.
Okay, thank you. Let me see. So we have, okay, now. Okay, so we have Anders who asked a question. Let me, or somebody's raised their hand. Now I got to figure out how to do this. So Austin, did you still want to, or were you the one who asked in the Q&A? I guess you could tell me in the chat. Anyway, let me go first to the, yes, okay, perfect. So Dakota, the question is, have you looked at Match Pro from the CDC?
No, I haven't. Match Pro? I have not.
Great, thank you, Austin. Maybe in the chat or in the question that you have, maybe you could give a link to it. It's always good to hear about other other options. Oh, and Austin said they used it during COVID in DC Health.
Yeah, thank you. I'll check it out. Always looking for other record linkage software to compare against.
Yeah, for sure. Thank you. Okay. Thanks, Dakota.
All right. Yeah, so moving forward, so the size of record linkage that we do at the census, we have to introduce blocking. So blocking is kind of a necessary evil that instead of comparing or matching on the entire comparison space, which is like computationally infeasible, we have to reduce the number of pairwise comparisons by using blocking first, right? Where we group records by like attributes before actually attempting to link those records. So I wanted to comment about how BigMatch, fastLink, and Splink implement their blocking strategy. So BigMatch blocks by this method of filtering, where you can set up multiple blocking passes. And how this works is if a link is made in a prior blocking pass, that link won't be made on subsequential blocking passes, and that comparison will be skipped. FastLink implements more of a traditional blocking approach, where it uses multiple blocking, so when using multiple blocking passes, you have to remove those redundant links that were printed. And then I really enjoyed how Splink's setup was. Splink blocks records using kind of SQL-like logic, which is, kind of akin to using group by statements or where statements. And what it does is it sets up kind of a union across all of these grouping conditions and sets up your comparison space in that way. So it's kind of instead of having multiple blocking passes in that way, you can just set up the set of possible comparisons that you would need to do before you even jump into the linking. And then for our experiments, we utilize the PES blocking design. And with that, there was a drawback with FastLink. FastLink wasn't able to actually use the original PES blocking design. So we had to loosen the blocking criteria for FastLink, effectively making a superset of the original scheme. So if you notice, like for example, on pass one, the PES blocking design says that we block on the 10-digit phone number. We modified the blocking scheme to only block on the 3-digit area code. And then for pass two, instead of blocking on state, county, CCU ID, first initial, first name, first initial, last name, we just grouped records by their state ID. Real quick aside, a BCU ID is Census's basic collection unit ID. So it's kind of akin to a block of houses or a neighborhood of houses. Going through these other ones, for pass three, we blocked on the first initial, first name, first initial, last name, month of birth, and date of birth. We just reduced that to blocking on the first initial, first name, first initial, last name. And then for Pass 4, we just reduced it to sex and age groupings. And what an age grouping is in this sense is grouping records of people who are in their 20s, people who are in their 30s, and people who are in their 40s, et cetera. The matching parameters that we used is we matched on first name, middle initial, last name, month of birth, date of birth, age, and sex. We didn't use any address characteristics for this because for the post-enumeration survey, we're trying to find records that could potentially exist at other housing units because there's this potential that a person is represented at a different address at census day. So we're trying to find these duplicates in that sense. So we're just using the person characteristics for our deduplication. And with regard to the matching parameters, BigMatch, we use the M's and U's, the matching probabilities that were used in the 2020 post-enumeration survey. We allowed fastLink to learn its set of M's and U's on the whole set of data that we fed it. So it was able to generate all the patterns that could exist within the data that we provided it. And then Splink was able to run its expectation maximization algorithm. However, with the SQL backend that we were using the DuckDB linker for that, and that was kind of a limited SQL backend that didn't allow for this kind of large-scale pattern learning on the entire data set, but it was able to learn the M's and U's on the blocked set of data, blocked set of comparisons. And then to go into detail about the data that we did the matching against, so we performed a deduplication on the blocks that contain the e-sample person records. What that means is the census unedited file, which is kind of this set of decennial respondents, the e-sample is a subset of that. And that subset was broken up between the United States stateside records, person records, and the Puerto Rico person records. And so for the US stateside records, the e-sample records was in the 1.1 million records. And for the Puerto Rico, there was about 33,000 person records. And then for our truth, to determine how well the individual software performed, we were able to utilize the clerically reviewed linked data from the post-enumeration survey. And so within this set of 1.1 million records, there was about 3,941 true duplicate links within the stateside data. And then within the Puerto Rico data, there was about 1,125 true duplicate links within this 33,000 set of person records. And here's the results. And I'll take a moment to describe these graphs a little bit so you guys can get your bearings in terms of how well the three software performed. So what we did is we measured the software's ability to like how high their F1 could be set based off of cutoff. So the Fleggy Center framework works by generating a match probability or a match score. And you have to set a cutoff to say pairwise links that have a match score above a certain threshold will be printed as a link, and anything below that will be discarded as a non-link, right? And so the way that we made these graphs is we set the cutoff for the candidate software to be set a little bit lower so that it would produce a large set of links. We sorted those links based off of their match score from highest match score down to lowest match score. And then we would determine that cutoff based off of the F1 at that given point. So the F1 being how well, or the number of true positives and false positives that are gathered up at that point. And so what we see here is BigMatch for the stateside in DC ended up getting the highest overall F1 for both DC and Puerto Rico. BigMatch also ended up beating out Splink and fastLink. Splink ended up coming in second, and then fastLink was a little bit behind. And then moving on to in kind of table form, and also a refresher for those of you guys, F1 is the harmonic mean of precision and recall. So precision is the number of true positives in the numerator plus true positives and false positives, so true links and bad links. And recall is the number of true links found over all of the links that could have been found. So you want to strike a balance between precision and recall to determine your kind of F1. And so for BigMatch, the bolded value is the winner for that column. So for timing, precision, recall, and F1, what we see here is BigMatch did perform the fastest for the US stateside results. fastLink ended up having the highest precision, but that's kind of with the caveat that the recall was so low. So what this is telling us is that fastLink did a really good job at finding good quality links. However, it was a little bit conservative in its willingness to actually find links out there, whereas BigMatch kind of struck this balance between precision and recall to generate this F1. With regard to the Puerto Rico results, again, BigMatch performed really well, had the highest precision for Puerto Rico, and then the highest overall F1, but Splink did actually end up generating a higher overall recall for the Puerto Rico at least.
Hey, Dakota?
Yeah.
Thanks. We have a question. What % of duplicates do you believe could be an error and are in fact not duplicates? And I was kind of thinking of a similar question or request, if you could expand on how you determined they were true duplicates.
Yeah. So this is kind of the big caveat here, is that what we're using for the truth is based off of the 2020 PES clerically reviewed matches. So like the error isn't really determined in that sense, or at least we hadn't kind of encapsulated it in that way. We just assumed that the clerical reviewer that had gone through an extensive clerical review was performing kind of perfectly, but that is the caveat, right? That, you know, there's still human error to the clerical review, no matter how much we, you know, prepared them in training and in the follow-up operations and things like that. So for what we're saying is true duplicate pairs out there, it's true duplicate pairs with the asterisk that those duplicates were determined first through an extensive computer matching operation and then through a clerical review that resulted in a follow-up that then went through another clerical review. So for the post-enumeration survey, we do a very extensive clerical review that I would say, you know, we're pretty confident in when something is labeled as a truth or as a true duplicate, it is a true duplicate for sure. But there's still always that caveat that there's, you know, human error associated towards that. And that's just, you know, what happens when you're working with real data, I guess.
No, that is true. I think that's one of the key issues with doing record linkage is getting a data set that has ground truth, so to speak.
Yeah. And we feel, you know, confident that this what we're using as this ground truth is a good ground truth relative to what else you have out there for labeled duplicates within data. So it went through, you know, an extensive follow-up operation, and the clerks, you know, did their due diligence when it came to labeling a duplicate.
Great, thank you.
Mm-hmm. Any other questions on the results?
Not that I can see.
Okay. Yeah, so we'll just do some concluding discussion. So the first part of it is BigMatch is a single-threaded application. So it's a C-based executable, but it is currently single-threaded. But it was still able to perform faster than the other two software. I kind of attributed this to, you know, doing the two-language problem of C versus an R or Python software comparison. The links, this is that caveat that we just talked about. The links that we used as truth were clerically reviewed, but and this is the other caveat towards maybe BigMatch's performance, is the initial round of matching for the 2020 Post-Enumeration Survey did use BigMatch. However, BigMatch was a part of a broader suite of record linkage software. It then went through a clerical review, that went through a follow-up operation, that then went through another clerical review, kind of to that extent. So the labeled true pairs are by no means constructed only by BigMatch, but BigMatch did play an initial factor in terms of determining the initial round of duplicates. The other thing here is that the legacy matching parameters that we use for BigMatch, it struck a really good balance between discovering true duplicate pairs from the truth, with the kind of not actually discovering some false links, or like kind of creating an acceptable level of precision, but it doesn't have this learning functionality of the expectation maximization algorithm. So we're kind of stuck with manually entering in matching parameters that have been used. I mean, it's just that over the several decades, they still do really well. And so, from, decades of research at the Census Bureau, those matching parameters that we are currently using are still high quality. This is kind of our conclusion on fastLink, is that fastLink was prohibitively slow for scaling to a deduplication set of, say, a nationwide deduplication task of 350 million records. So our initial goal on the outset was to try to see if we could get fastLink to run on the whole cuff to deduplicate the whole 350 million records, but based off of how big or how fastlink's blocking design is, with its parallel computing being done at the block level, it kind of made things prohibitively slow. And to describe what I kind of came across in doing this, the way that you set up the blocking with fastLink is you use this block data function, and it creates these blocks. And depending on your blocking rule, your blocks can vary in size. And so having parallel computing saying allocate 32 cores for this process, some of those blocks may be small, and some of them may be big. And so the way that it's allocating CPUs can vary. And so it causes throttling effect, as I describe it. And so that's one problem. The other problem was going through each of these blocks, it made a for loop. And we know that with R, a for loop is slow. And there are ways to parallel compute for loops within R, but balancing the built-in parallel computing of fastLink with parallel computing of a for loop would be a little bit of a challenge. And then with regard to Splink, all of the results that we showed were using this DuckDB blinker. This is kind of the off-the-shelf, the first SQL backend that you can use if you're running things with Splink. But there's other SQL backends out there that would allow for parallel computing on a larger scale, such as if you're using a PySpark backend. And so that is something that we're looking towards utilizing in the future to see if we can scale Splink to larger record linkage tasks on larger sets of data. And this will be a point. I'll stop for questions, and then I have that demo that I can shift over to.
Sounds good. I don't see any new questions in the chat or in the Q&A. So go ahead. I really like how you've explained some of the differences between the tools.
Yeah. You guys can still see what I'm sharing, right?
Yep.
Okay, perfect. So just what I wanted to do, since this is our Govys, show an R package running record linkage, and you guys will have Ted Enumerato next month, so that's very exciting. What I'm doing here, fastLink on RL 10,000. So this is just a Jupyter notebook. For those of you guys at Census, I'm just running this on the DSCE, the Data Science Community Environment. It's in my home directory, and all I have in it is just this notebook and this CSV called RL Data 10,000. And for those of you guys who are interested in doing record linkage, this is a very good starting point. This data set is a synthetically produced data set that has kind of a labeled set of true links within it.
Oh, I'm
And
sorry, Dakota, I'm going to interrupt because somebody just raised their hand.
yeah,
Stas, I'm going to allow you to talk. So hopefully I did that right. Oh, there you are. Okay, good. Go ahead.
Okay, can you hear me?
Yes. Mhm.
Awesome. Yeah, so I've been working with Dean Resnick on rewriting and others within on rewriting NorcLink into C and Python. So our experience is that the bottleneck is the pair formation. So it implements a variation of Feligesanter. So, but what takes the longest is the pair formation. Have you looked into kind of figuring out where the bottlenecks are in the compute? Is it possible at all in any of those packages?
yeah, so the bottleneck, okay, so real quick, let me just to prove to people. So I'm going to restart and run this notebook just to give you guys an idea as this is running in the background and I'm addressing this question. So for the bottlenecks, with specifically for fastLink, bottleneck is in the blocking. And then like for the bottlenecks on Splink, I don't know if I can really confidently say where we're seeing those bottlenecks quite yet, because our current goal is we got limited by the DuckDB backend, and we know that backend wasn't intended to be used for larger scale record linkage tasks. So we hadn't started profiling, I guess, Splink at that point to determine where certain parts are slowing down. With regard to BigMatch, which is, I mean, Dean Resnick would know about BigMatch and kind of its behavior, but the benefits of how BigMatch works is it has the smaller file read into memory, and then the larger file, the kind of record file, is kind of this index file. And so with regards to the efficiency that is made by BigMatch relative to these other two software, is it seems that the other two software holding the data and handling the data is being held into memory and could potentially inflate slowing things down, whereas BigMatch has this really efficient means of pulling in the record from the record file to compare it against the memory file and go through that kind of incrementally in a very add in memory, deallocate the memory manner. Is that kind of, I'm not sure if I'm fully addressing your question, but those are kind of my initial thoughts with regards to where the bottlenecks exist. For fastLink, for sure, the bottleneck exists within the blocking currently.
Hey, Dakota, I wonder if some of the slowness could be due to the EM algorithm and estimating the probabilities that BigMatch doesn't do.
Yeah, well, no, okay, yeah. So that's all caveated with how we did the EM algorithm for both fastLink and Splink, because yeah, BigMatch does not run this unsupervised learning, is we didn't time fastlink's and Splink's ability to learn on the patterns that exist in the data. We allowed them to learn a set of parameters ahead of time and then just read in the EM object for when it came to the linking stage, if that makes sense. So we weren't timing, when it comes to the timing of Splink and fastLink, we were just timing the linking stage of the thing. But yeah, that is a good point, that like there's a cost associated towards generating the M's and the U's, the patterns that exist in the data, the unsupervised learning step that would happen before the linking actually occurs. That's
really good to know. Thank you. That seems a fairer way to compare them.
Yes, yeah. And I guess with that, so what I was saying here with this test data that we're doing, this RL data 10,000, there's 10,000 records, and within it, there's this 20% overlap. So 8,000 of those records don't have a duplicate pair. 2,000 of those records do have a duplicate pair. So that means that there's 1,000 true links that exist and need to be identified in this set. It's 1,000 because if you think about like the handshaking lemma and graph theory, if A matches to B, B also matches to A. And so there's 1,000 true links to be found in this data. And just to give you guys an idea of how it looks, we've got a first name, a second first name, a last name, a second last name, year of birth, month of birth, day of birth. And then there's a record ID, which is really just the row ID. And then there's an entity ID. And the entity ID is the label of whether or not that link should exist. And this is just saying there's 10,000 rows. And just for the sake of example, this is what a duplicate pair looks like. So Han Schmidt and Hran Schmidt. And the issue here is that there's a typographical error here in Hran's, but they have full agreement on birthday, birth month, and birth year. And then there's missing information. There will be missing information in the first or in the second first name and second last name, because not every record will necessarily have a second first name or a second last name. And as we were talking, I ran a fastLink in the background. So calling the fastLink function kind of looks like this, where we assign data frame A to be that RL data 10,000, data frame B to be the RL data 10,000. The matching attributes that we're using, first name, second last name, year of birth, month of birth, day of birth. And then we specify what we're going to do for string comparison, which is those named attributes. We can specify if it's a duplicate matching run, if we're matching data frame A to data frame A. And then we set a match threshold to be 0.9. So any match score that is above 0.9 will be printed as a link. And then number of cores for the parallel computing, I specify it to be 4, but what we see down here, and this is kind of one of those things where the way that fastLink is designed, this OpenMP doesn't really seem to allow us to have much control over the parallel computing. Depending on the size of the task, it may just say, hey, you don't need all 4 threads for this process. The other thing that it says here is it identifies, it says, hey, DFA and DFB are identical, so we'll assume deduplication of a single data set. So that's nice to see that it's saying that to us. But when it came to, oh, I would like to utilize 4 cores for this, it just used 1 thread. And with regard to how that kind of played out for our actual matching, is some of those blocks would allocate enough resources to utilize as many cores as we specified it to be run on. At most, we were running on 48 cores for a block if the block was big enough. But then if a block became too small, it would just kind of throttle down to doing what we see here, where it was like, we'll only allocate 1 thread for this particular block. And so with regard to like the bottleneck of how fastLink kind of currently works is you handle 1 block at full throttle, and then you get to a smaller block and it slows down, and it doesn't actually do all of the distributive computing that you'd hope. But at least with regard to this run for the 10,000 to 10,000 comparison, it ran in about a minute. What it produces as an output is this list of lists. It has a list of matches, which is the kind of the indices that they matched on. And this is something else that I didn't like to see on the duplicate side of things, but we see indices 1 and 1 matching, 2 and 2 matching, 3 and 3 matching, 4 and 4 matching, and then we see 4 and 1,957. So what this is telling me is that it's still making the trivial comparison, meaning it's matching row 1 to row 1, even though I said, hey, well, let's do this deduplication. So this might be a user issue on my end, or that the deduplication is still doing the trivial comparison, which is not kind of what we would hope for. I'll skip this part and jump down to it right here, just to say, so to Wendy's point on, hey, if fastLink and Splink are doing the learning, how is it fair to compare fastLink and Splink to BigMatch if BigMatch doesn't have any learning to it? what we could do ahead of time is you can, there's a specification in the run of fastLink to say, hey, I would like to save the EM object, and it will just run the expectation maximization algorithm on the data, and then it'll save the EM object, and then you can later plug that EM object back into later runs for fastLink. And so this is what the EM object looks like. And to go over it with regard to like how it relates to the presentation, we have this P.M. That is our lambda probability. So the probability of given any two pairwise comparison that those two records actually end up matching. There's some rounding done here, just using the kind of display structure command. So this is actually really a value like 0.999, yada yada. The other things that I was talking about with the M's and the U's. So since fastLink is doing these levels of full disagreement, partial agreement, and kind of full agreement, these are the three levels that we generate for the M's, for the case attribute. So for the first name attribute, we get these three M levels, and they increase in match probability as the attribute becomes closer to full agreement. And we only see those kind of three levels for the named attributes that we're doing, the first name, second first name, first last name, second last name. And then for the year of birth, month of birth, and date of birth, we just have an M or a U, they agree or they disagree. And then notably to like kind of gauge how well the expectation maximization algorithm did in learning on the data, we're using month of birth and day of birth as a matching characteristic or as a matching attribute. And so if you were to ask yourself, what's the likelihood of you coming across any one person who you know who has the same month of birth as you in agreement? That actually is this 1 in 12, and that's what this U probability is right here for the month of birth. And then what's the likelihood of you coming across any old person who has the same day of birth in agreement with you, and that's that about 1 in 30, 1 in 31 probability being right here. So it's just kind of a simple way to gauge that how well the EM was actually learning, as you can kind of make sense of the U probabilities. That the U probabilities kind of adhere to how you would think the distribution of the those particular month of birth or date of birth matching characteristics look. And then the other thing I guess I wanted to show here is the patterns that actually get generated from the pairwise comparisons. And so this also shows the level. So 2 is the highest level, and then 1 is the middle level, and 0 is disagreement. And so so 2s across the board, there was 5 cases in the 10,000 to 10,000 comparison where there's full agreement across all 7 of the attributes. But the most kind of common agreement matching attribute that we see is right here, where we have full agreement in the first name, full agreement in the last name, month of birth, date of birth, and year of birth, or sorry, year of birth, month of birth, date of birth. And then there's missingness in the second first name and the second last name, right? That not every record will have these attributes populated with information. And then as we would kind of expect, down here, the pattern that has the largest count is things where there's full disagreement in the first name, nothing in the second first name, full disagreement in the last name, nothing in the second last name, and then they disagree on year of birth, month of birth, and date of birth. So that's kind of within expectation, right? That the vast majority of the records that you pair or you compare together will not agree. And so this is kind of an indicator that, yeah, okay, these patterns that you're seeing in the data with these pairwise comparisons is, I guess, makes sense. And then to kind of finish off how I'm setting up this, this is leading to the graphs that I made. I wanted to represent the output as linked output, so I call them edges. So this is what a kind of typical edge or a link would look like. So row 7,718 linked to 7,333 with probability 0.999 yada yada. And so record A's first name was Petra, record B's first name was Petra, so there's full agreement in the first name, full agreement in the second name. And then when we're looking at the last name, we see Hoffran and then Hoffman. So there is a little bit of disagreement in the second last name. However, we get the supporting evidence for the second first name. And then for the second last name, I'll scroll down a little bit, scoot over. There's full agreement in the second last name. So for this record, sure, there's a typographical error in the last name, but all of the other attributes have full agreement. And so this record ends up having the highest overall kind of match score associated with it. And that's, you know, it has its second first name and its second last name populated with information. And as I was saying, when constructing these F1 graphs, I sorted the score in descending order. And what we see at the very bottom, of this output is there's these links that have probability 0.92, right? And there's agreement in the first name, there's agreement in the second first name, however, the last name completely differs. And we also look over towards like the month of birth, date of birth information. So they agree on year of birth, but their month of birth and their day of birth are different. And so this would be a false link. And the way to check that as well is we'd want to see if, to check if it's a true link or a false link, if A entity ID and B entity ID are the same, it's a true link. That's a true link. That's a true link. And we would expect all the true links to exist at the top of this, this output. And then at the bottom, we start seeing instances where there's disagreement in the entity ID. And from there, that's where we compute the F1. And as we're collecting up the top scoring links, our F1 rises and rises and rises. And eventually, after we collected up so many links, we're starting to collect up false positives. And so our F1 starts declining. And so at that peak F1, if we hold on to 1,058 of those links in that top output that I was talking about, we would get an F1 of 0.9572. And that cutoff, or we want to set the cutoff to get that F1 score, is at 0.9970. So anything with a match score above 0.9970 we'll hold on to, and anything below it we'll throw it away. And then the last little bit here is some summary information. So if we do set that that threshold to hold on to just that 1,058th link, we'll end up finding 985 of those true links, with holding on to 73 bad links and leaving about 15 links on the table to be discovered. And that was all run in about a minute. So, yeah, that's what I wanted to show you guys in terms of how fastLink can kind of be run on a data set. So if there's any other questions, feel free to ask.
Yeah, there's two questions, but I have to say this is really super helpful because I need to start jumping into fastLink and figuring things out. So I really like how you explained that table with the different configurations. I think it was, yeah, the one higher up with just like the zeros and ones and twos and yeah, that one. Just to, you know, showing how, okay, it makes intuitive sense, you know, what's happening. Super helpful. Thank you. We have two sort of questions. First, I'm just going to read the statement. This is from Stas, and I think he had to jump off, but he said he wanted to mention that in his experience with NorcLink, data sets of about 100,000 plus test cases from the record linkage package, which was another package somebody else mentioned, that they see 80 to 85% time spent on pair formation and EM would not be a
Mhm.
problem. I said they've been trying pandas and polars on the Python side to compare speeds, and they're about the same. He said wasn't sure what they had on the R side, because I guess DuckPlyer or DuckDB, not sure, wasn't out yet. Okay, and then somebody had a census specific question. I don't know if you could see it, Dakota, but I'll read it. If the,
Yeah, if you could read it.
oh, you can read it? Okay, good, because sometimes when
Oh,
it's,
no, sorry, I was gonna ask if you could read it.
oh,
I
okay.
can,
Yeah, sure, I'll read it. I'll go slow. It says, if the reference file has an individual with multiple PICs, which is I think it's a personal identifying, it's a unique ID. Okay, they said that.
Mhm.
Say an ITIN holder received a social security number. So I guess that person would have two sort of unique IDs, right? Will this individual ever be matched across surveys after receiving their social security number? Or are they forever unmatchable?
So with regard to the reference file, if the PIC exists, it's protected identification key, but I think people generally also think like person identification key, but what it is it senses unique identifier for a record through the PVS process done by ERD. So if on the reference file that PIC exists on multiple points, it's a unique identifier. So I would deduplicate like on unique PIC ID. So I don't think that's actually addressing your question, but there is like the PIC master file, right? That has the I guess the set of all PICs that are assigned to individuals. And I would think that since that PIC is a unique identifier, you would deduplicate. And when I'm saying deduplicate in that sense, I'm thinking collect up distinct PIC IDs, not actually probabilistic record linkage, but just like count up the unique distinct PIC IDs before then doing the record linkage. But the thing about with PICs is the record linkage has already been done. So if you're trying to match, say, a PICed survey to a PICed reference file, at that point, all you do, right, is do a join. And I don't know if that's actually addressing your question, though.
Yeah, thank you for correcting my definition of a PIC. So, yeah, so if I'm reading this correctly, it seems like they're saying the example is a person has an ITIN and then later gets a social security number. So would they be, I mean, how would that work in future surveys or deduplications or something?
Yeah, if there's, I guess if it's asking if there's error in the PIC, so if someone it's a person who is represented distinctly between two different records, and they are given a PIC ID under a social security number versus given a PIC ID under an ITIN, and they're two different distinct PICs, that would be kind of error in the picking process. And I guess probabilistic record linkage, if you aren't doing the matching on PIC and you are doing probabilistic record linkage in this sense to that reference file, you generate kind of what I would say is like this V shape. So one record in file A matches to two records in file B. And that would be a potential indicator of that those two records should be duplicate pairs of each other, even though the PIC IDs are different from one another, if that's, so it'd be kind of a way to address how well the picking is done. I think it is known though that we were talking about how this theory of record linkage is done through the Fleggy Center framework, and the PVS, which is assigning the PIC IDs, is also using a Fleggy Center based record linkage approach. And so I guess if we're doing a BigMatch match to the data versus a pick match to the data, the overarching understanding is that both of them were done through the Flaky Center methodology. Now, whether or not they used the same matching attributes is a different thing.
Yeah, I suppose, I mean, I don't know, I'm guessing, but maybe if the records were matched not on any kind of unique IDs, but based on what you said, like last name, first name, birth date, birth year, that's like ignoring any kind of IDs, right?
Yeah. And that brings up like the thought of, say, if a person gets married and they change their surname and things like that, that if you have a unique identifier associated with that person, such as a social security number, yet their surname changes over time, maybe record linkage isn't going to do the best because the last name is different between the old record and the new record if the surname has changed.
Yeah, that's why record linkage is fun, right? Because there's all these
Mhm.
challenges.
Yeah.
Okay, great. Thank you. Well, it's 4 o'clock and this was a fantastic discussion. Thank you so much, Dakota. I really appreciate it. And I think it's as I said, we sort of had this theme going on with record linkage talks for our Govys. Maybe I'm a bit selfish having these because it's something that I'm working on here. So it's something I'm learning about. So it's been good for me, hopefully good for our colleagues out there working on statistics and R for the government. All right, great. Or not just for the government, but whatever they're doing. Okay, thank you so much, Dakota. I really appreciate it. And I'll get in touch with you about slides, if you could share slides and maybe your Jupyter notebook or something. No pressure if you can't do it, but we'll be in touch by email that way. And
Yeah.
thanks
Yep.
everybody. Oh, go ahead.
Oh yeah, no, just yep. I feel free. I'll share out my slides in my my notebook for you guys. So.
Great, thank you. I think I'm going to use that to learn more about fastLink. All right, well, thank you again, Dakota. I appreciate all your patience with getting things scheduled and working right. And I really appreciate it. It was a really interesting talk and very informative for me and hopefully for others. All right, thanks again. And we'll be in touch and hopefully we'll see everybody next month and share the word about our Govys. Thanks again, Dakota.
Thank you.
You're welcome.
Bye.
Bye, everybody.